Hello everyone. The topic Robometrics has chosen to explain to you guys today is Spur gears. Now, what are gears? All of us at some point or the other have been exposed to gears. It may be in wall clocks or the gear system of an automobile. Today we'll talk about spur gears and its various properties according to the strength. Eventually, we'll go through the design procedure according to the strength of the spur gear. So, coming to the procedure, we have in all 14 steps with us, starting from selection of material, assuming the life of gear, calculating its various properties like Young's modulus, bending stress, compressive stress, and finally, we'll be calculating the induced stresses. And if the gear conditions are satisfied, we'll find the other parameters. We see that there are so many page numbers written over here. So these page numbers are of the design data book, which is compiled by the PSG College of Technology. So we'll get most of the values from our data book only. I have summarized 3 points which we'll have to remember by heart. So assuming the life of gear, which is point number 2, we'll take any value between 10,000 to 25,000 hours. Point 5 is the selection of K naught according to shock loading. So we have 3 values here. If application is specified under moderate loading or heavy loading, or if it is not specified at all. In point number 8, we'll be needing the value of Z1. So Z1 is assumed according to the condition specified in the question, either full depth 20 degrees, stub teeth 20 degrees, or full depth 14.5 degrees. Now full depth 14.5 degrees is a special case which is rarely used. Mostly we'll be seeing either full depth or stub depth. Now we'll have to remember this point. Over here Z1 is greater than or equal to 17. So to be on the safe side, we'll take Z1 is equal to 20. And for step depth, we'll take Z1 is equal to 16. Now directly jumping onto the question, we need to design 2 spur gears which are used for rock crusher drive and to be of minimum size gears. The power transmitted is 18 kilowatts, speed of the pinion is 1200 rpm, angular velocity is 3.5:1, tooth profile is 20 degrees stub teeth, which we just saw. And assume that gears are made of case hardened alloy steel. Now this is a very important point because as you know, the first step is selection of material. So from page number 8.5, we will be selecting case hardened material. Now there is a correction in the book. We see under the heat treatment column, the carburized and case hardened have to be interchanged. So case hardened becomes 15Ni2Cr1MO15. This is the one we'll be selecting for the question. Step 2 is assuming the life of gear. So let us take 20,000 hours. We could also take 25,000 hours or 15,000 hours or anything, but here I am taking 20,000 hours. Third step comprises of 3 things: Young's modulus, bending stress, and compressive stress. So Young's modulus is given on page 8.14. As we see in table number 9, for pinion 1, material steel and Young's modulus is constant, which is 2.15 into 10 to the power 6 kgf per centimeter square. Converted to Newton per mm square would be 2.1 into 10 to the power 5. Next we have bending stress given on page 8.18. Now we'll consider rotation in one direction. So the first formula over here, design bending stress is equal to 1.4 divided by n kbl upon k sigma into sigma minus 1. Most of the values in this equation can be found on the very next page. So we'll be going to table number 19. Under alloy steels, we see that sigma minus 1 is equal to 0.35 times of sigma u plus 1200. So sigma u now can be found out from 2 pages, either page 1.40 or page 8.5. From page 1.40, we'll be getting a value of 1040 Newton per mm square, and page 8.5, under the same material, we'll be getting 900 Newton per mm square. So to be on the safe side, let's take the higher value, which is 1040 Newton per mm square. Now if you see, I have converted 1200 to 120, so that my answer comes in Newton per mm square. So now my sigma u is 484 Newton per mm square. Just below table 19 we have table number 20, which is factor of safety or the value of n. As we see, our steel is case hardened steel, so let us choose the value of n is equal to 2.0 under steels and heat treatment is case hardened. Continuing further, we have the value of stress concentration factor for the fillet K sigma in table number 21. Now again, as we know, case hardened steel has three values: when x is less than 0, when x is greater than 0.2. If none of the conditions are given, we'll choose the center value, which is K sigma is equal to 1.2. Coming to table number 22, which is given on 8.20, we see that the surface hardness of our material is greater than 350 from page number 8.5, which gives us life in number of cycles as either greater than 25 into 10 to the power 7 or less than 25 into 10 to the power 7. So we know that life is the number of hours it has worked into the RPM. So I'll write 20,000 hours, converted it into minutes, so multiply it by 60 and then the RPM, which is 1200. So my answer becomes 144 into 10 to the power 7 cycles, which is obviously greater than 25 into 10 to the power 7. Therefore the KBL value which I will be taking is 0.7. But we have a twist over here. Just under the table we have a note. The note says if the case hardness HB is greater than 350 and the core hardness HB is less than 350, which we can see from page 8.5, then the coefficient KB is obtained for HB is less than 350. So HB less than 350 but greater than 10 to the power 7 cycles becomes KBL is equal to 1. Hope you guys got this. If you have any problem, the comment section is just for you. You can freely ask anything over there. So putting all these values in our original formula and multiplying them, we get design bending stress as 282.3 Newton per mm square. The third part is compressive stress sigma C, which is given on 8.16 and 8.17. So coming to 8.16, under the table design surface sigma C, we see that we have two formulas over there for calculating sigma C. We will be choosing the formula which has CR in it. So my formula becomes design sigma C is equal to CR into HRC into KCL. For calculating the value of CR, we'll look into table 16, coefficients CB and CR, and under the wheel material we find alloy steels, which is case hardened as per our given condition. So the value of CR becomes 280. Now HRC can be chosen between 55 to 63. So here I will be choosing the value of 60. To calculate KCL, we'll be coming to the next page 8.17 under table 17, the life factor for surface strength KCL. Now for the material steel, surface hardness HB greater than 350 and life cycles greater than 25 into 10 to the power 7, life factor as we see is 0.585. Therefore, my sigma C design becomes 9828 kgf per centimeter square or 982.8 Newton per mm square. Step 4 is assuming the value of KKD. Now KKD would be used in step number 6. So we will assume the value of KKD as 1.3. Step 5 is the shock loading condition, which I had told you on the very second page of this tutorial. So we see that the application is rock crusher, therefore heavy loading. So we'll take K0 is equal to 1.5. Sixth step is computing the design torque, MT, which is given on page 8.15. So under the table of design twisting moment, we see MT is equal to nominal twisting moment transmitted by the pinion into KD into K. Now we have an addition over here K naught, which was 1.5 as we just saw. To calculate the nominal twisting moment, we have a formula in relation with power, which was given in the question. P is equal to 2 pi n mt divided by 60. From here, my value of mt comes out to be 143.23 Newton meter. Substituting this value in my design MT formula, I have 143.23 into KKD, which is 1.3, and K naught, which is 1.5. My value resulting as 279.39 Newton meter. Now let us calculate the center distance A given on page 8.13. So for the formula of spur gears, we have this formula. A is greater than the complete thing. Now we know the value of I as 3.5, which was given in the question. Value of E is 2.1 into 10 to the power 5, sigma C, I, and design MT, all of which is calculated. Now there is a new variable called psi, which we assume as zero point 0.3 over here. Solving this, my value of A becomes 142.38 mm. So we are halfway through right now. Continuing step 8, we will find the Z1 according to the given conditions. So the tooth profile is 20 degrees stub, therefore Z1 is greater than equal to 14. As I told earlier, we will be choosing a little more than this value and an even number, so Z1 is equal to 16. At the same time, I can calculate Z2, which is I into Z1, or 3.5 into 16, which turns out to be 56. Now let us calculate the module M and then standardize it from 8.2. The formula for module M is given on page 8.22. So we have the value of A, which we just found out, and the values of Z1 and Z2. So my module becomes 3.95. Jumping onto page 8.2 right now, under the table recommended series of modules, under the preferred one column, there is no 3.95. Therefore, the next value which I'll be choosing is M is equal to 4. Now since my module is standardized as M is equal to 4, I will have to revise the value of A. Again on page 8.22 using the same formula, I will be revising the value of A. So A is equal to 4 into 72 divided by 2. 72 is Z1 plus Z2, which gives a value of 144 mm. Similarly, I will be finding the value of B over here, which will be used further on. So as I know psi is 0.3 and A I just revised as 144, therefore B becomes 44 mm. I also need the diameter of the pinion, again given on page 8.22. So D1 is equal to M times Z1, or 4 into 16, that is 64 mm. Pitch line velocity V is equal to pi D1 N1 divided by 60 into 1000. I have divided the equation by 1000 to convert the D from mm to meters, so that my final answer is in meters per second. So here I get a value of 4.02, which I can round it off to 5 meters per second. Finally, in step 10, we have the last thing to calculate, which is psi p, which is equal to B by D1. B I just found out to be 44 mm and D1 as 64 mm. So dividing these two, I will be getting 0.68. To standardize this value, I will be jumping to page 8.15. The bottom left table over here, I see a table for cylindrical gears. So here psi p is equal to B by di, as I just told you. So my psi p standardized value becomes zero point 0.8 over here. As I see next to the psi p column is bearings close to gears and symmetrical, which is also known as K. So The value next to point 0.8 is 1.06. So my new K value becomes 1.06. Step 11 is the highest quality of gear given on page 8.16. So let me assume the highest quality of the cylindrical gear as 8, and my pitch line velocity which came out was 5. So I see that there is no 5 as a given value in the columns. So let me choose the value as 8 over here. Therefore, the value of KD can be found from IS quality as 8 and pitch line velocity for spur gears as 8 again, which leads me to the box 1.4. So the value of KD I'll be requiring in the next step is 1.4. As I told in the last step, from 8.15 the value of K came out to be 1.06 and the value of KD comes out to be 1.4, assuming IS quality as 8 and pitch line velocity as 8 again. Now let me revise the value of my design torque. So MT, as we know, is 143.23. K becomes 1.06, KD is 1.4, and K naught remains for shocking load condition as 1.5 only. So my new value becomes 318.82 Newton meters, or 318.82 into 10 to the power 3 Newton mm. Finally, let us calculate the induced stresses from 8.13 and 8.13a. Compressive strength is given on page 8.13. We'll be using this formula, sigma c is equal to this one, where we know the value of I, E and MT. Also we know B is equal to 44. So my value comes out to be 1022.84 Newton per mm square. From step 3, I calculated my design compressive strength as 982.8 Newton per mm square. Now the induced strength can never be greater than the design strength. So my compressive strength condition is not satisfied. So we'll have to do one more iteration for that thing. Now let me just check with the bending strength conditions. So 8.13a gives me the formula to calculate sigma b. Over here, I think all of my values are known except the value of y. Now what is y? Y is given on page 8.18. Y is basically the form factor. So now I know that the value of Z is 16. So moving on in the 16th row to the 0th modification, we have the value as 0.355. I won't be looking at the negative values or the positive values. I will be just checking the 0 condition because nothing else is given to me. Now I have to just keep one more thing in mind. Just below this table, I have one condition written in star. For height factor f0 is equal to 0.8 stub teeth, the above value should be divided by 0.8. Therefore, I will be dividing my y value by 0.8. Now I get the value as 127.78 Newton per mm square, and my designed value was 282.3, which is greater than the induced value. Therefore, this condition is satisfied. Since my compressive strength condition was not satisfied, I can do 3 things over here. One of the option would be increasing the value of m from 4 to 5. So if I choose the value of m is equal to 5 and continuing from step 10 onwards only, my values for a, b, d1, v and psi change like this. Therefore, my modified value of sigma b becomes 66.54 Newton per mm square and sigma c becomes 738.63 Newton per mm square, which is obviously less than the designed sigma c, which came out to be 982.8 Newton per mm square. Thus, both my conditions are satisfied. So after increasing the module m is equal to 5 in trial 2, the design becomes satisfactory. Once my design is satisfactory, I will be jumping onto page 8.22 to calculate various other parameters like the bottom clearance C, which is given by 0.25 into the modulus, that becomes 1.25 mm, tooth depth H, which again becomes 1.25 mm, tip diameter by using this formula becomes 17.6 mm, and the root diameter by using this formula, which all of which is given on page 8.22, becomes 69.4 mm. So don't worry guys, if your design is not coming as satisfactory, you can always write a statement that by increasing the module to the very next value, the design could become satisfied. Hope you liked this video. It was a long explanation. Stay tuned for more videos on various different concepts on transmissions. Please click on the subscribe button if I was able to explain all the concepts to you. Robometrics.